Good afternoon, all. It is a great privilege to introduce you to Peter Bühlmann, our final keynote speaker. Peter is a full professor at ETH. I think he's very well known. His research is in mathematical statistics, but very much at the interface to machine learning, computational biology, and similar topics. He has published a lot in multidimensional statistics, computational methods for large-scale modeling, and also, I think, in the last several years, causality. I think it's fair to say that Peter is one of the leading statisticians of his generation, and he's received many, many awards. I won't list them all, because otherwise we would be standing here for a long time, and Peter would get increasingly embarrassed, so I'll stop. So Peter's talk will cover, I think, very nicely his research. It covers, I think, clinically very relevant application combined with statistical ideas about how to transport predictions across different domains. Peter, the floor is yours.
Thank you. Okay, thank you, Marcel. Thank you, the organizers, for having invited me here. It's a big honor also to be here and present this lecture. Being the last speaker here, I certainly appreciate that you still have some interest to come and attend my lecture. So here's again the title of my talk: Learning from Other Intensive Care Units, Can We Improve Statistical Predictions? So let me first acknowledge maybe the main collaborators in the research. I will explain a bit today. This is Dominik Rothenhäusler, Xin-Wei Shen, Armin Taib, Malte Lonchin, Jonas Peters, and Nikolai Mainshausen. It's about prediction in ICUs. So we have intensive care units. We live in the age of digital medicine, digital health. A lot of data is measured, and there is also this word, what people say, AI in medical care, AI in digital health. And somehow the question I ask is, do you really trust these predictions? Now, of course, some of the machines will work very well. Others may do not work so reliably, and this will be somehow a bit a topic and aspect of my lecture. I should say there are important developments just generally in the field that people started to realize this is a problem, so we better make sure to have some sort of certificates of AI systems, of algorithms, of machine learning. This will be very valuable in the future. I'm not working in this area, but I think this is a very important direction. I will not say too much about it any longer, but the FDA, also the European agencies, they have that. They really care, and by good reason they care more and more what the machine learners, the algorithmic people actually spit out and claim it works well. So certification of software, of algorithm pipelines is a crucial and important step. My field is more the AI in medical care in terms of methods. I think it's challenging. I want to show you a bit what we're working on, and perhaps I want to convey a few statistical ideas, what we try to do and what we try to achieve. So here is my running example. This is a conceptual example. This is on real data. We actually have 4 very large databases which we harmonized. We also made this more publicly accessible to the extent we can. The problem is about a certain response. This is just one among many possible responses. This is the average heart rate in the 3rd day after the ICU entry. Okay, maybe some people have left, but some people stay for 3 days. You want to predict the average heart rate. There are covariates in the problem. There are 4 static covariates, sex, age, 2 others, and there are quite a lot of dynamic averages of covariates, like how does your blood pressure behave and so on and so forth. So we have 50 of those. The training data is approximately 200,000 samples from about 200 different hospitals in the US. This is the so-called eICU database. This is fairly public, and with our software tools, you can actually also access that. Now my goal, my conceptual goal is I predict on a new hospital, on another one. This is a large hospital in Boston. This is the MIMIC 3 data. This is also public. And I make this example conceptual. I say, okay, I want to predict in Boston with 0 samples or only a few samples available from this Boston hospital and see how well I can do. So the Boston hospital is not among the 200 in my training data. This is a conceptual goal. Maybe it is a proof of concept how difficult and to what extent domain adaptation in medical applications is possible. In computer vision, domain adaptation is quite successful. It's probably much harder to bring this in the medical context. Why is it conceptual? Of course, the Boston hospital has a lot of data, so we just keep them away and want to see how well we can predict, and then we can evaluate, right? So how would you model that? How to make accurate prediction, and if I have time, I say a bit something about interpretation as well. Okay, so I guess you all have heard about the classical mixed models with random effects, and that's what comes to your mind. I have 200 hospitals. Every hospital is here indexed with this little e. E goes from 1 to M. M is 200. I have 200 different hospitals. I have my response in hospital E. I model that as a fixed function of covariates. Then I add a random effects term. This is linear here for simplicity. This is not important. And then there's an error term. This is a classical approach. And then you ask, okay, how would you use that model to predict on a new target, a new hospital? The new hospital is here denoted with E prime. This is my hospital in Boston. I want to predict that on a given covariate X. And if you look at the mixed models literature, this is very closely related to what people call empirical Bayes. So let us assume we typically have few data from the target hospital, from the Boston hospital. I denote that data by D target, and I can estimate from these few data my fixed regression function, non-parametrically or with machine learning or whatever you want. You can do that, but you only have few data, so it will be very noisy. On the other hand, you have training data. You have this large training database with 200,000 observations, 200 different hospitals from these 200 heterogeneous sources, and that data is denoted by D training. I can also estimate in that model my fixed effect function from this large database. This is f hat based on training large database data. Now, if you have a conditional Gaussian distribution, the best estimator for my hospital in Boston, the y hat E prime, is just a convex combination of the individual estimate you have at Boston and of the estimate which you have received from your large or based on your large database. So this is very well known. This is what you can do. You can also think of this. You do L2 norm shrinkage towards the estimate from your large database, right? Now, this conditional Gaussian assumption, of course, is not important. It works much more generally. You can say, okay, I have few data points in my Boston hospital. How I do make the prediction? I do my estimation there, but I shrink my prediction towards what I have observed or gotten from my large database with over 200,000 samples. So this is well understood. This may work well. And also I should say, if you have no data at Boston, so you just have a new hospital, you want to do the prediction, this approach amounts to you simply take the fixed effect estimated function from the large training database. That's it, right? So if you have no data from the new hospital, essentially what this would tell you is, okay, you use some sort of non-parametric function estimation, you use machine learning, say based on a least squares principle, just on the large pooled data, my 200,000 samples from the 200 hospitals. That's what it is. Okay, so this is actually what you should do. If you believe your mixed effects model is a good model, is approximately true for your large training database, and if this model also holds for the new data in Boston, then you should follow this rule, and that's it. And you can read it in many textbooks. There is software for this, so this is quite great and good. So the question is then, does this really work? And we have some sort of empirical results that you can improve on that. And the question amounts to, is it really just an additive random effect which distinguishes one hospital from the other one, and so on and so forth? And also, if you go to the new hospital at Boston, is it simply just an additive, simple random effect? Perhaps this model is too simplistic. It may not be appropriate for the truth, and we need a different perturbation model, and I will also introduce and explain a bit what we do in this area. We will also show empirically that other perturbation models can indeed perform better on this task. How well can I do the prediction at the Boston Hospital? I'm not saying this is an overall best machine, but we're interested to see, do other perturbation models, other models modeling the heterogeneity from one hospital to the other, from one medical center to the other, would they perform similarly or actually better than a classical random effects model? However, I actually wrote in my abstract, I tried to build up also the fundamental thinking about this. The empirical base perspective will still remain to a certain extent, and I will explain that a bit later. Okay, so what I want to do is reconsider a bit how we model heterogeneity, also look at how well does it generalize to new hospitals like Boston, what is the robustness, and if I have a bit time, can I say something on interpretation? So let me start here in a fairly simple fashion for the moment. Let's assume I have data. This is maybe even a smaller data set. The data comes in numbers, in vectors. I denote them by little z1, z2, zn. And in statistics, we always interpret these numbers as outcomes of random variables, random vectors. They're denoted by cap z1, cap z2, cap zn. The simplest model, perhaps much too simple, is IID. It could be another model, like could be from a stationary distribution, and so on and so forth. The point is, in this modeling paradigm, we have an underlying probability distribution, which is the data generating distribution, right? This is denoted here with P0. And my goal is kind of a bit absurd, actually. Now, I want to say something about a new probability distribution, which would generate new data, like in my Boston Hospital, which is different from P0, the one which I have in my data. If I can do that, my analysis is what people call externally valid to a certain extent. Even though I have data only from P0, it even holds if the new test data comes from P prime, which is different from P0. Now, this single P0 is too simplistic. In a moment, I will give you an example how we make this more realistic. So if you want to say something about a new P prime, which is different from P0, and you have data from P0, this is, of course, in general, absolutely super ill-posed. You can do nothing against it, right? Nevertheless, people since a while actually have worked on this problem under various keywords. One is distributional robustness. Maybe P prime is not that different from P0. Transfer learning, domain adaptation, transportability, this is more a causal concept, and so on and so forth. So quite a few researchers have worked out quite a few solutions what you could try to do. So this was my announcement. Now I don't look at a single data generating distribution P0. I look at a slightly more maybe realistic setting in practice, which also matches my ICU example. I assume that I have heterogeneous data from different distributions. This is denoted by PE, and this little e is a medical center, a hospital, a subpopulation, an environment, and so on and so forth. And in my presentation, this little e in script D is the space of different medical centers, hospitals, environments, which I observe in the data. So in my ICU example, I have 200 different hospitals, so script D is encoded by 1 to 200. And now slightly more general than before, now I want to say something about a new PE prime, the data generating distribution, where E prime is not among the observed medical centers which you have in your data, right? This is just a generalization from before. I want to say something on the Boston Hospital, even though maybe I have zero data from the Boston Hospital. Okay. Again, this is what people call external validity, and in my talk, the script D, these are always the observed medical centers, and what's outside script D is external. So, I want to say something about a new PE prime, my Boston Hospital, which is not in my training data. Let's look again at mixed models. What would happen here? If you would think the mixed model would be the true model, this would simply say, okay, the new E prime, the Boston Hospital, comes from the same heterogeneity than what I have in the training database, these 200 other hospitals. Could be, maybe not. And it would also say what I said before, it would just mean it's an IID perturbation over these different heterogeneities, E from 1, 2, 3, and so on. And so I questioned that already, and we really want to do something different. So just to make the point clear, I think this is something which happens in great generality, certainly in the medical health context, multi-center study with diverse subpopulations. Eventually, you're not interested to say something about people in that subpopulation. You want to say something about new people which you've never seen in the study. It's kind of obvious. There's one nice writing by Davis Cox. I'm quoting him. This was in his comment to Leo Bryman's The Two Cultures paper, became quite interesting paper between the difference of statistics and machine learning. And Cox wrote, the success of a theory is best judged from its ability to predict in new contexts, something which is outside. Okay, you may also ask, well, does it really matter? And this is quite an interesting study by the Stanford group. They put out the so-called wild Stanford database, and they want to see how well does machine learning works in terms of external validity. So you train your machine learning algorithms on some sort of training database, maybe several of those, and then you try to predict on a new data set which is external, which was not used for training, and the new one may have a bit of different distribution than the one you used for training. So you can look at this little table here. There are these different databases. In the first left column, there's performance metrics, various metrics. So large means good. Large is a good prediction. There's this column in distribution type. This is kind of like cross-validation. You have your data, you delete some data points, you see how well it does. That's in distribution. You're still looking at the performance not in a new context. And then out of distribution, they have this additional, say, environment which has been left out, and then you see how well it can predict. And then you see there's a performance reduction from in distribution 47 to out of distribution 31, then from 93 to 70, and so on and so forth. So on average, there is a 26 performance reduction from internal cross-validation type to external. And so this is a nice documentation. This is also what people believe. Machine learning techniques are quite sensitive. And if you go a bit external, their performance decreases rapidly. So it is a real issue, what we're talking here about. Okay, so the question is, how should we then model these perturbations? If it's not a random effects, mixed effects model, what else can we do? And I show you one kind of framework how to do that. And I start with this. Okay, this is, of course, a super ambitious picture here. But this is like an oracle would know what's going on. It's a model for the entire system. I have a response variable y of interest. I have explanatory covariates x. I have many non-observed hidden variables. They can be very annoying, right? Because they can give unobserved confounding all that is known to the oracle, and the oracle would know how these variables connect to each other. Of course, you cannot infer that from data, but suppose you would have it. So this is the structure which the oracle gives you, and now if you have such a graphical information, people do a quantitative model on this graph, and this is well known under the heading of structural equation model. So you say that these different nodes in the graph, these are random variables in the system, and every variable is modeled, and that comes down in the slide. Every of these nodes is modeled as a function of its parental node, comma, error term. It could be an additive error, a multiplicative error, and so on and so forth. I have a couple of variables in the system. This is here denoted with this W, and then through all the components. So if I look at all these nodes and random variables jointly, I have all these error terms, and you make one assumption, namely, these error terms are jointly independent. Now, people in causality, in particular also Judea Pearl, call these structural causal models because he makes this big philosophical step that this structure here, this reflects the true causal system. I prefer not to do that, and I just call them structural equation models. This is just much more, much more a model which I want to use. Whether it's causal or not, that doesn't matter to me. So Pearl and the causality people call it a structural causal model. I just call it a structural equation model. These are exactly the same models. That's not important. And you can ask, well, are these good models? And for example, they have a nice property. If you look at these random variables jointly, they generate a distribution, and that distribution is Markov with respect to this underlying graph. So this is perhaps a nice property of these models, but not really crucial for my ICU prediction problem. So what I really want to make very clear in this talk, I'm not trying to learn this graph. This is a very, very ambitious task. It cannot be done unless you make very restrictive assumptions. I only use these structural equation models to model perturbations, right? And I'm not claiming any truish causality here. I use causal language, but I make it for using something completely different. I just want to model perturbations. I'm not claiming we do anything which is closely related to causal. I think it's good for some of you who don't quite know how these perturbation models go to give you a bit of glimpse of idea what's going on here. And I want to explain to you the simplest perturbation or intervention model with such structural equation models, and I want to give you a primer on Pearl's do intervention. It's important to say, from my perspective, this is only a model, and the model goes as follows. So on the left-hand side, you see this graph. Here it has no hidden variables. Suppose somebody gives you the graph. And then you can write down the structural equations to this graph. So you can see every node, for example, the y node, is a function of its parental variables, x1, x2, comma, error term. And all these errors are jointly independent. Now we make a perturbation, an intervention into the system. And Pearl writes this as, for example, I intervene at the second node. And he writes do x2 equals little x. So do x2 equals 2.7, you set x2 to the value 2.7. So what happens now? There's no true answer, there's only a model. It's important to say, now I tell you a model what happens if you set x2 to the value 2.7. The model says, okay, look at the graph. It's very plausible. If you manipulate at x2, the arrows which go into x2 should be deleted, right? Because you just set this x2 to 2.7, hence there is no arrow going into x2. That's plausible. And then you have this adjusted or modified graph, and then you write down your structural equation according to that graph. In particular, x2 in blue is set to this little x, like 2.7, and then this 2.7 value propagates through the system. So it influences x1, it influences y, and through x1 it influences y, and that's written down here. Okay. So why am I showing you this? This seems kind of entirely technical. There are two properties with these perturbation models. The first property is, this is what I call dynamic propagation of an intervention. You intervene in a system somewhere, and then something happens to all the variables in the system dynamically. It propagates further along the structure of the graph. This is a very good property. This is a very realistic property in many real systems, I think. And there's a second thing and property or assumption which happens here. This is called autonomy. I haven't told you, but now I'm telling you, if I do this intervention at the second variable, I change my graph, I write down my structural equation models, but what is assumed here is that these functions remain the same. I have the same functions, f1, fy, and so on. And that is, of course, a huge assumption, right? So probably a bit unrealistic, but if you want to make external prediction, you have to extrapolate somehow, and so that's one of the main assumptions this perturbation model does. Now people say, yeah, okay, there are other perturbation models in the causal literature. That's true, and essentially all of them have these two properties. The first, a very good one, dynamic propagation of interventions. That's, I think, quite realistic. The second one is a huge assumption. You just assume that the functions themselves do not change. It's only the values of the nodes which change. So this is a model. Now, Pearl says, okay, now we can do causal thinking if you have such perturbation models at hand, because causality is giving me a prediction, a quantitative answer to a what would happen if I perturb? What would happen if I set x2 to 2.7? If I know the system, I can compute it, right? That's good. There are these two underlying assumptions and properties, and I refer here to this really path-breaking work by Judea Pearl. Therefore, you can say, okay, causality can be used to generalize to new scenarios. I can now generalize to my Boston hospital. I just use this causal machinery. That's it. Okay, honestly, this is yet just another model for perturbations. I'm not saying this is somehow the true model. There's the true causal mechanism. Some people do that. I just say, instead of a mixed effects model, I use or look at another model, which is this kind of perturbation model, to model heterogeneity, model how one hospital differs from another one, and so on and so forth. And that model has interesting properties, and I want to show you that a bit. And to do that, let's make this all a bit more operational, and then I show you also how this works on this ICU prediction problem. As I said before, just as a recap, I consider heterogeneous data. I have 200 hospitals. I have a regression classification type problem, covariance X, response Y. They all depend on your E, the hospital or the environment or the subpopulation. So the example, the medical ICU data from the 200 different centers or hospitals. Okay, so far so good. Now we go again. This is a recap. I do this external validity. I say, okay, how about hospitals which have not been in the database? These are many possible non-observed centers, environments, or perturbations. And in my notation, they come from a class of perturbations, script F, which is much, much larger than what you see in the training data. So the script F, for example, in the ICU would be, I have the 200 ICUs in my training data, and then many other hospitals which I don't have. And the goal is prediction. I want to predict Y given X, as usual. Somebody gives me a covariate. I want to predict the response. But I want that this prediction works well, is robust, not only in the data which I use for training, but also externally outside in this script F. Okay, so here's again my prediction problem, and for simplicity in this talk, I look at linear models only. We have extensions for non-linear models, for machine learning algorithms, but let's just discuss all this for linear models, which is also much more clean. So if you want to be good for all these other perturbations or scenarios which you have not seen in the data, you might look at, if you mathematize this, you might look at the worst case risk, the maximum over all possible interventions or perturbations from this script F, and then you optimize this worst case risk, right? You look for the regression parameter beta, which optimizes the worst case over future medical centers. Okay, so people say, well, that's robustness, right? That's true, sort of worst case risk optimization. And some people say, well, this is causality because it is about interventions, perturbations, which you have never seen in the data. And then you say, okay, well, what's better here to use? And this is one of the big messages in a way. The things are the same, actually, and this was quite surprising until a couple of years ago. So if you look at linear models, it is actually a theorem, a mathematical fact that worst case risk optimization, I try to optimize my worst case risk over a class of heterogeneity, perturbations, this solution to my worst case risk is actually what people call the causal parameter in the causality literature. If, and now the assumption of that fact is if this script F, your perturbation model satisfies a couple assumptions, otherwise this is hopeless, right? So this is a theorem. The main assumption is if F is of a certain form, then this holds. So why do I make this so important? I think it's important to say people do risk optimization all the time. They do least squares in linear model, that's risk optimization. So it's something we're very familiar with. Not many people do causality. Well, okay, it becomes more popular and so on, but it's still a bit an exotic field somehow. And this is actually the same, if F has a certain form. So that's why I think it's interesting and also powerful. So now I should tell you just a bit what this F actually is, and of course I don't do this very technical. If F are all possible perturbations which do not act directly on my response, but they dynamically propagate, then the theorem is true. And here is a picture of that. This is graphical. I have X, it's multidimensional. I have a response Y. Here are my environments, my different medical centers. If they act only on my covariates, but not on my response directly, then the theorem is true. Worst case risk optimization equals the causal parameter. So there are surely some experts here in the room and say, yeah, well, this holds under much greater generality, and that's true even if there are hidden variables in the game. They're very nasty, right? You don't like hidden variables in statistics. Even if you have hidden variables which confound your whole stuff, if your perturbations, if your medical centers only act on X, but not on Y and not on the hidden variables, how do you know? But if you assume that, the theorem is still true. Worst case risk optimization equals the causal parameter. So I think this is quite interesting. And so for people who work a bit in this area, they would say, okay, this is covariate shift. This is what happens, and you should consider that in your ICU prediction problem. Maybe only my X's shift from one hospital to the other, but there's no direct effect on my Y. This may be quite questionable, but if that would be the case, this is what I have here in these graphs. The different perturbations, the different medical centers only act on X. It's only shifting my covariates. Maybe I should explain this slide very quickly. So why is this true? And I always refer to this person, Trygve Havelmo. So he was a famous person in economics. He later got the Nobel Prize in economics. And Havelmo in 1943 derived in my terminology, the following. If somebody gives you the causal variables, if you have this graph, right, somebody says this and this is the causal variable, then if you look at the conditional distribution of y, but you condition only on the causal variables, that conditional distribution will remain the same over all possible perturbations which do not act directly on y but on x. So Habermas saw this quite early. So he said, okay, if you would have causal knowledge, you can make systems much more robust, stable, invariant. And that's kind of plausible, right? I should make the point clear, if you condition on all your x's, that's not true. If your x's change, your conditional distribution will change. So you really have to have the knowledge of these causal x's. Okay, so we kind of know now, if you have these assumptions that your perturbations make only covariate shift, I can look at causal parameter, or I can look at worst case risk optimization, and then I have a very good method. But that's not really working in practice so well. And why is that the case? The problem is this mathematical language of worst case risk over all possible perturbations. These are too many, right? In practice, your perturbations may not be arbitrarily strong. They may just differ a bit from one hospital to the other, and it's not a good idea to go for this worst case risk optimization over arbitrarily strong perturbations. And that motivated us a bit to what we call causal regularization, and this is also what we will then use for this ICU prediction problem. So instead of trying to make things as invariant as possible over the different environments, we just regularize towards making things more and more similar, such that the conditional distribution remains more or less the same. And let me try to explain this a bit in words and formulas. I make one switch. So the environments from before, these were these E's, they are now outcomes of a random variable A. Okay, and you will see later why I call this A. But instead of E, a different environment, a different medical center, I call it now A. And now what you could do, and what's not a bad idea, is to say, okay, I run my linear model, but I estimate my parameters such that the corresponding residuals here are fairly uncorrelated over my different medical centers, right? And you do this inner product of A times the residuals, and you can solve this. This is very easy to solve. So this is the idea. You just run least squares, or you run machine learning techniques. You run them on every hospital, but you make it such that the residuals do not look that much different, and you can penalize this more or less with this regularization parameter xi. A version of that, and this is actually what we implement also in software, is what we call causal regularization. Instead of this inner product, you look at the projection onto the column space of A. This is like in least squares, a linear projection. And you estimate your parameter as anti-projection residual length squared plus a regularization parameter gamma times projection residual length squared. Okay, this is a recipe. And you can ask, well, what is this doing for us? If you set this regularization parameter gamma to 1, this is just least squares. Why? This is Pythagoras. You can always decompose the squared error into anti-projection length plus projection length. And for general values of gamma, this is just something I might call this causal regularization. Okay? Now you say, okay, linear models, well, I can add any sort of sparsity enforcing penalty. I can do lasso, I can enrich, I can do group lasso, I can do all these things computationally very easy. It's all convex. And this is really very simple. It's not here on the slide, but you only need to linearly transform your y and x and then stick it into your ordinary software, and that solves this problem. So it's very, very easy to do. Now you ask, well, why should you do this? And this is what I explain quickly. It has kind of nice mathematical guarantees And you ask again, under what conditions? Nothing comes for free here. And I look again at this problem. I have y, I have x, I have hidden variables, I have these a's. These are my different hospitals, and the question is, how do these a act on the system? This is what we had before. This was this instrumental variables regression model. The different environments act only on x, is only covariate shift, but it does not act on y, it does not act on h. It's a very famous model. It has a very big assumption. The different environments do not act on h, they do not act on y directly. Nevertheless, I should point out, instrumental variables recently received a Nobel Prize in economics. It's a very, very important model class where people can make interesting contributions. So the Nobel Prize went here to Angrist and Imbens for their path-breaking work with instrumental variables models. So we remove this assumption. We say, okay, I really try to find models for perturbations. Why should I say that the perturbation does not act on y or h? Let's just allow for all of this. So my perturbations act on x, h, and y, on anything. The only assumption which we make, there is still an assumption, is that this A is exogenous. This is what people in economics would say. A is external, or in the graph, A is a source node in the graph. All arrows point away from A. And so we gave A a name, we call it an anchor node, and that's why we denote it with an A. Okay. So if you have this graph structure, it's quite general. My different hospitals, they have just external forces which drives the difference, but these forces can affect everything. Now you can put a model on the graph. If it's linear, it's a linear structural equation model, like this one. And if you look at this is not just covariate shift, and this is certainly more realistic. This is what I call everything shift. Okay. So for people in domain adaptation, this is quite an important thing. You don't assume it's just a covariate shift, or you don't assume it's just a shift on y. Everything can shift. Okay, so good perturbation model, but in that model you can never get to the causal parameter. That's well known. I will not say much about this. So why should you do it? The reason is we still can do this, or should do this, because this causal regularization still solves for a worst-case optimization problem, where this script f, the perturbation, the heterogeneity which I have in my data are of a certain form. Okay. So I think that's an important message in view of time. I think I will not explain too much about the math here, but the important point is I have now a fairly general perturbation model. My hospitals can act on anything. My only assumption is it is an exogenous force which comes from one hospital to the others. If I do that, I get interesting robustness results, and I don't have too much time to talk about this, but if you do this worst case perturbation risks in such a model, which I just described or indicated here, you can actually prove, and so I'm skipping details, that this worst case risk over a class of perturbations equals exactly the objective function of your causal regularization, namely anti-projection residual length squared plus a regularization parameter gamma times projection residual length squared. So this regularization parameter gamma, I skipped some of the details here, is actually nothing else than how strong is that perturbation. So if you have a lot of difference in heterogeneity, a lot of difference in perturbations from one hospital to the other one, you should choose gamma large. If you have very homogeneous different centers, gamma will be small, and so on and so forth. But what I want to say is that kind of model allows you to deal with everything shift perturbations, and we get robustness out of that. I'm not claiming any causality in this context, But I want to say this kind of machinery, which is extremely simple to use. Okay, it's here. That's the machinery. You just linearly transform the data, gives you very powerful robustness properties. Okay, so now I want to show you how does that work. I mean, you say, okay, is it worth the effort, right? And actually, we tried here quite a bit. This is not finished. So we have 4 large curated databases, so we were quite early to do that. We have also a nice R package, the RICU package, and so on. So we will continue to look into that, but now I want to show you what we actually achieve. Okay, so this is my prototype problem again. Why is the average heart rate in the 3rd day after ICU entry? I have 4 covariates, static ones, 50 dynamic ones, training data 200,000, 200 different hospitals. So these 200 different hospitals are my 200 different environments. I can use them as my anchor variable in my causal regularization. And if I do this, I look how well can I predict on the Boston Hospital. And this is the mean squared test error here as a function of how much you use this causal regularization. So gamma equals 1. This is here on the left side of the plot. This is least squares. This is just ordinary pooling the data, just run your machine learning algorithm and pool data and see how well you predict on Boston. That's the naive approach. Now, if you increase gamma, you make things more invariant, you make residuals more similar from one hospital to the other, then you improve. And then if you make gamma too large, if you make it more and more the same, the residuals, then it's bad again. And this is actually what these more causal techniques do. They go for full invariance. The conditional distribution just remains the same. That kind of corresponds to gamma very large. So what you can see is there's a certain gain from here to there, and then it gets bad. Now you can look at the 90% squared error quantile. This looks the same. Gamma 1 on the left is the naive approach. You take your large database, you run your machine learning algorithm, you predict. If you increase gamma, you do see performance gain. If you make gamma too large, it will be bad again. Now, don't ask me how to choose gamma, because I have no data on my Boston hospital. Okay, this is not the very realistic thing to do. This will be very hard. This is what I call agnostic extrapolation. You get some sort of data, there is a new thing, the data is not really representative for the new thing, you're just purely agnostic, try to do that prediction, and that's what comes out. Okay, of course it's much better if you have some data from the target domain, maybe only a few. And this is what I assume here. I have few n-prime data from the target domain. That's also very standard in the success stories in domain adaptation. And now I run my empirical Bayes idea. And that makes a lot of sense to bring this old technology coupled with these new perturbation models. So what we do is, okay, I have my target data from the Boston Hospital. Maybe n-prime is just 50 data points. I run my least squares on the Boston Hospital, but I shrink the least squares estimator towards this beta hat gamma, and this beta hat gamma is my causal regularization from my large database, right? You choose a certain gamma, and then you can do that. It's very simple to do. Now, because I have a few data points on the Boston Hospital, I can use cross-validation on the new target domain to choose the hyperparameters. Okay, how does that work? Oh, no, sorry. So why do I call this empirical Bayes? Just to make the connection. There's a prior distribution, there's the data, there's a posterior distribution. The prior distribution is for the target domain. This is what I assume for my Boston Hospital. I somehow have it. I have data from the target domain. That's also good. And with that, I can get to the posterior distribution for the target domain for my Boston Hospital. I have also data from my training domain from the large database, and I can use that to estimate my prior. So I estimate the prior distribution, that's why it's called empirical Bayes. for the target distribution with my large database. And what I do here, I take this robust approach with these perturbation models. We just estimate the parameter with this causal regularization instead of just standard pooled least squares. Then I have data from the target domain, and then I can compute the posterior for the target domain with the estimated prior from the training. And if you assume Gaussian or conditional Gaussian, this is exactly the procedure what you get. You just do L2 norm shrinkage from your estimation based on few data from your Boston hospital towards what you learned from your large database. Okay. I think this can be seen. So let's look at how well can we do as a function of how many samples I have in my target hospital. Okay? I have many in my Boston hospital, but I just first choose 25, 50, 75. I want to see how well I can do. So this is actually for the Boston hospital, and the green line here is the performance, the mean squared error. You could look at different performance metrics. This is the performance if you only use the data from the target domain from your Boston hospital. If you have few data, you're bad, and if the number of data points increase, you will get better, 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 okay? The red line here is this, what I just showed before. This is this empirical Bayes procedure. If you have not many data from the Boston hospital, you do substantially better. Eventually, you will not be better. And these flat horizontal lines, they are agnostic. They have no data from the Boston hospital. And one is just pooled regression in gray, and the other one is this causal regularization in blue. So we see already a gain here, but you can do, of course, much, much better if you have a few target data left. So this is kind of successful for the Boston hospital. Now you say, okay, let's look at others, not only the Boston, let's look at other medical centers. This is one in Switzerland, this is another one. What you see is the green curve. If you only use target domain data, it improves if you increase the number of samples, and eventually it is about as good as if you used a large database from other ICUs. Now here, for these two other hospitals, there was actually no gain in doing this complicated causal regularization business. You could just do pooled least squares, anything like that. It worked as well. The point is, on the Boston hospital, there was gain. On the other two, there was no gain, but also no real loss. So this is on the 90% quantile of the absolute error. This is a function of this gamma. And you can really ask the question, was it worth doing this causal regularization over a mixed effects model and do empirical Bayes? And for this Boston hospital, the prediction on the Boston hospital, even if you have a few target data from Boston, it is worth going through this more complicated exercise. For the others, it didn't play any role. So what I find interesting and worthwhile is to point out the following, and then I stop. How much can we actually learn from other ICUs? Now, this is on the 4 international databases we look at. I'm not making any general claim, but you can ask, well, how much information can you borrow? And our answer so far is quite consistent. You can borrow up to about 1,000 samples from the target domain. So if it's an absolutely new hospital which has no patients, that's great, that's good. If the hospital has about 1,000 patients already, there's no information any longer in these very, very large databases. We can take all 4 together, so we can have 1 million samples. It's just not more worth than 1,000 samples from your target. So we found this quite interesting. There is value in trying to learn from other ICUs, but the value, if you measure it in terms of my own currency, is 1,000 samples. That's the value you get. The proposed empirical Bayes method with this causal regularization was always among the best. Sometimes it was not better. For this one hospital, the proposed empirical Bayes was clearly better. This is maybe what we expect from a robust procedure. A robust procedure is maybe good in the bad cases, and in the good cases, it's not better than using standard methods. Let me conclude. Learning from other ICU data, in our examples, I repeat myself, it's about worth 1,000 samples from the target hospital. Distributional robustness for external validity can help. If people are interested in this problem, so we have this RICU package, and we spend actually a lot of time with PhD students also harmonizing 4 major databases. This is the EICU and the MIMIC. They're both from the US. The HIRID is from Switzerland, and the Amsterdam, obviously, is from the Netherlands. So each of these databases has, again, different hospitals and so on and so forth. So it's quite an interesting set of data which we have. And it's hopefully a good source to make further progress in this area. Generalization to new domains and subpopulations is hard, it's not easy, and we should understand standard ML is not really good at it, it's very sensitive, so that's at least the state of the world so far, and this robustness and invariance causality are related in certain settings, which opens interesting paths maybe also for developing new and better methods. Thank you very much.